So closing our session is Alessandro Perelli. Alessandro is a lecturer at the University of Glasgow, and he will be giving us a talk on stochastic multi-resolution image sketching for inverse problems.
Thank you for the introduction and for the opportunity to present this work with Matthias Herhard from the University of Bath. So it nicely followed the problem of the previous talks on model-based optimization, but mostly focusing on computational aspects. I will introduce the concept of dimensionality reduction and how to obtain this from an image domain perspective. And so we'll present this IMASC or image sketching algorithm and some results on numerical simulation for CT problems. Now again, just to set the scene, I'm considering a linear model where X is the unknown vectorized input, RD. And then we have the for operator depending on the application. So this is an M times D matrix with some particular structure, and then with isotropic noise. So this can fit with different imaging modalities. Again, the noise can be different, or the forward model can have a specific structure. Now, we are focusing here on the maximum a posteriori problem, where we want to minimize an objective function which has a data fit term. Here, this is for the L2 norm because of the isotropic Gaussian noise, plus a regularization term to impose the structure. Now, from a computational perspective, if we exploit first-order solver, the bottleneck generally, even if we use handcrafted or learned regularizer, is in the computation of the gradient of the data fit, especially in this term in red, because we have a big high-dimensional matrix, D times D, which is K adjoint terms K, which needs to be updated every time because X changes at every iteration. Now, there have been a lot of research on subspace embedding, so how to design matrices which operates in the measurement domain, so S, such that we can have an embedding that preserve the distance between the sketch version and the original one in the measurement domain in a radius of epsilon. Unfortunately, the problem is that most of these sketches, for example, random Gaussian sketches or leverage score, does not fully utilize, for example, the structure that K can have, I don't know, maybe Fourier domain in MRI. And so this product can not be very efficient. And also there are some restrictive bounds on how many, on the dimensionality reduction, so on the rows of S. So the question here is, can we instead leverage fast and deterministic image domain multi-resolution sketching operator and then design a solver that can leverage this, meaning that randomly select this one of this multi-resolution operator in an iterative fashion. So now we will explain our, let's say, idea on to design this sketching operator and then the solver as well. So the idea is to design a family of operators that they call SI, which significantly, which are much cheaper respect to KX. So as you see here, S now is applied on the right side of K. And then what we want is that this new operator should not introduce bias in the solution. So we want that the expectation over I should be equal to the identity. So basically the idea is that this Ki operator, the sketch version of K, should be similar to the original K. Now, a simplest choice would be to pick the decimator interpolator. So an easy choice is to define this decimator Ti, which goes from full resolution images, so square of D times square of D, into a low resolution grid. So in this case, if we take I equal to 2, we have a 4 times 4 block that we map as block averaging into 1 pixel in the low resolution domain. And then the sketch is effectively the T adjoint times T, which is proportional onto the subspace of piecewise constant images. So we have this Ti, so this is a family of low resolution mappings doing by block averaging in this way. So this is an example from an X-cut phantom. So if we do block averaging, here you see, of course, all of them are 512 times 512 resolution images. So this is T star I times T. But the key important thing is that the last sketch, which is the full resolution one, you see is much sharper than the ground truth, the original one, because we want to compensate for the loss during which we have for the low resolution one. Now, when we apply the operator, we have a family of operator ki, where on top we have from 1 to r minus 1, so without the full resolution. This is k times six. Now, the important thing here is that practically we never compute ti adjoint. So, for example, if you're working on, I don't know, X-ray, this operator here, k t star, will be equivalent to the ray tracing between a low resolution grid in the image domain to the measurement domain. And so what we actually do is to apply R, can be, I don't know, an Astra operator in CT, on the low resolution block average image grid. And for the full resolution here, we apply this operator SR, which comes from the constraint that we have on the expectation. So we want that the sum over the sketches to be equal to the identity. So this is the example of the sketches in the measurement domain. So on the left, we have the full kx star. In the middle here, we have the sketch version of it. And at the end, you have the full resolution one. Again, you see how sharp it is to compensate, let's say, the low resolution one. And at the end, we have the error between what we have from the full resolution k in the measurement domain minus the sum of the, let's say, sketched version of the sinograms. Now, why we are interested in this? So, for example, in this example, I will concentrate on CT reconstruction. So we use Astra operator, and for a 2D fan beam geometry, we run a simple multi-Carlo simulation. So here in the x-axis, you have different image resolution, and on the vertical one, you have the computational time. So you see a quite nice linear fit between so input dimension and complexity. And so this explains why we are interested in using low resolution operator to make fast iterations. So by plugging in this new model into the original map problem, we have this new data fit function here, and we don't, and then the regularization, which is again acting on the full resolution X. Now the problem here is that the objective function now is not linear anymore in the sampling probability, so we cannot use, for example, stochastic gradient descent to solve this objective function. So this is when essentially we want to turn this problem into a saddle point problem, such that we have in this regime a linearity, the linearity property is preserved. So just to maybe most of you know saddle point and saga, just to give a brief ingredients. So we need to compute the convex conjugate function of our data fit term. So now this becomes f star. And when we change into an equivalent min-max problem, we have this new cost function where we want to solve respect to x. For the CT problem, we also impose a non-negativity constraint on the solution. Now, interestingly, compare, for example, with the stochastic primal dual hybrid gradient, we have here that y is not indexed from I, because I for us is exactly the sketches in the image domain. So from, again, a structural point of view, what it does, so for each iteration, k, we sample one low resolution, I, then we compute the gradient here for the primal and the dual. Here is to keep the memory. and then we apply the proximal operator for G and F star to update the primal X and dual Y variables. We have also convergence because we want to convergence. So we have this term here, theta, and this is k, so the iteration k. Just to say that this term depends on the operator norm of the full operator, so on your essentially forward model, but also on the Lipschitz constant of the stacked operator of the different low resolution sketches. So we apply this solver for a monoenergetic CT transmission problem where we define essentially a Poisson noise and then the exponential form for the Beer's law. We took the standard way of weighted least square, so we approximate based on taking the log of our measurement, and then we consider an anisotropic Gaussian noise with the inverse of the covariance is the diagonal of the sinogram S. So here are just the details of the simulation settings. Basically, we use Astro and ODL operators in Python to run this algorithm, and then on 512 times 512 2D images. Now, on the L2 regularization, we apply this IMASC. So here are the number of sketches. So the low resolutions that we used are equal to 1, is equivalent to full resolution operator. So we see here is the distance to the optimizer, where the optimizer is the solution to the primal dual hybrid gradient. And here is the root mean square error respect to the ground truth. So in both cases, this support the fact that if we increase the number of sketches, so the number of low resolution, we have an improvement, so a decrease in the computational time. So these are full matrix multiplication here. And this is visually, so if we fix the time, so 100 equivalent full matrix iteration, this would be the visualized XCAT phantom image at this budget of time, and this is after 1,000 iterations. So if you fix a time budget, this would be the achievable accuracy that you get using a different amount of sketches. We also try, even if our theory doesn't apply for non-smooth regularization, we apply TV in practice, and again, we got a similar trend in terms of error versus computational time, so full matrix multiplication. And this is the qualitative results with a clinical scan 2D CT image from APM as well. So as you can see here, intermediate images from after 250 matrix multiplications. Interestingly, again, for people who know Saga, very often we can add this extrapolation term so to add some memory here, and we found that this is very beneficial in terms of speeding up the algorithm, and especially to reduce also the variance. So these are the numerical results of IMASC-SEC, so using this extrapolation. So we see that the variance that previously was very high is reduced, and still, if we increase the number of sketches, we have benefit in terms of reduction of computational time. And this shows so the orange one is IMASC with extrapolation using 8 levels of low resolution, and the other one, red and blue, were the one without extrapolation, so IMASC without, let's say, memory. And the green one is the primal dual hybrid gradient, which uses only full operators, K. And so we can still show that with this extrapolation, we can, on the stochastic way, we can achieve, I mean, if you see, let's say, if you draw an horizontal line, the same accuracy with the less computational time. So in conclusion, so I show like a way to essentially reduce the computation, making sketches in the image domain, and then results on CT, 2D reconstruction with L2 and TV regularization. Now the future challenges will be to demonstrate that this can be also effectively applied to, for example, 3D data on different geometries like cone beam, CT, and higher dimension, and also extend, for example, to nonlinear model, nonlinear operators, and of course, different also noise model respect to Gaussian model. Thank you.